Well. Aika võiks tulla. Ma ei tea, hispaanlased läksid kodusest. All right, we are more or less ready to start. Toma, can you hear me?
Yep, all good.
Okay, so let's start. Mike will join. If not, then we have lecture recordings. Yeah, I did not send you last lecture screens, I think, but I'll be sending them both of today. Video recording is up anyways from last time. So rain formation in warm clouds. So what does it mean? Warm is that droplets are in liquid state. Otherwise they are cold, but if it is liquid state, then they are warm. And so now let us start from the very beginning. So perhaps you have noticed that cloud boundary usually bottom is very flat, but the top is puffy and not flat. So do you have an idea why is it like that? Why we have a flat bottom but fluffy top? Anyone? Yeah, Otto, what is your idea? Toma, do you have any idea why it is like that? Bottom is flat and top is fluffy.
Never thought about it actually.
Yeah, as a matter of fact, I myself also thought quite late about it. So I think I was doing my PhD in Moscow, and then I was in my lab asking that, okay, guys, different topics to discussing, and so, okay, well, why is it like that? And then one of the supervisors said, oh, well, that's obvious. And actually, it really is quite easy and simple why it is flat. So, now, having been given hints that this is obvious, do you have now a better idea? Okay, let us start. I'm giving you step-by-step hints. So, why do we have clouds at all? Why there are clouds? How they are formed? What are clouds made of? You surely have flown through clouds by plane. Okay. Through clouds by plane. So what are clouds made of? Very, very simple question.
Water droplets.
Water droplets, exactly. Now, how are these water droplets formed?
Condensation.
Condensation, exactly. So when starts condensation happen? What is needed for condensation?
Temperature gradient.
Temperature gradient? Yes, kind of, but you are stepping at overleaping one step, I guess. So do you know what is a dew point? Dew point. If you look into weather forecasts, weather reports, sometimes they tell you also dew point. What is dew point?
It's a temperature related to humidity, but I'm not sure exactly what.
Temperature related to?
Humidity.
Yeah. So what is dew?
The bits of water on the grass in the
Yes,
morning and
yes. The water on the grass. So when will it be formed?
Sorry?
When will it start forming?
in the morning.
Morning, yeah. What happens in the morning?
Sun rises.
If sun rises, then it's no, the dew is going away. Yeah.
It's getting colder.
Yeah, it is getting colder, yes, because of heat radiation, Earth loses heat and it is cooling. And until temperature falls below dew point. And so when it falls below dew point, a condensation starts. In other words, it means that saturation pressure becomes equal to water pressure, water vapor pressure. So in here you have water vapors. They have a certain partial pressure caused by water. So you know that that's Dalton law. You can separate pressure into contributions from different types of molecules, and so there is also water vapor pressure. So when water vapor pressure falls below saturation pressure, then there will be oversaturated vapors which start condensation. All right. And dew appears on grass, but there is also mist. So if temperature in the air itself falls below saturation point, the dew point, then there are also some so-called condensation centers in the air. So if it is very clean air without any dust, microscopic particles, without microscopic particles whatsoever, then water cannot start initially forming, even so water vapor pressure falls below saturation point, and then this is oversaturated vapors, which can have quite a bit. So relative humidity is water vapor pressure divided by saturation pressure. So this describes how far we are from dew point. If we are 50% humidity, we are very far. If we are 99%, we are very close, but still not yet there. 100% is dew point. 101% is oversaturated. When you have very clean air, you can have maybe 105% or something like that. But normally you wouldn't, because normally there are some dust anyways. And then there is dust, and then mist is starting forming. All right?
So what is the saturation pressure around 0 degrees Celsius?
Good question. Now, let me think, maybe on the order of 1 to kilopascal, I think. if I'm not very wrong. So at 100 degrees Celsius, who can tell me what is saturation pressure equal to? We are recapping basic thermodynamics right now.
Well, it's probably atmospheric pressure.
Yeah, it's atmospheric exactly, because so what is boiling? 100 degrees of Celsius is boiling point. So boiling is that inside water, bubble can start forming and growing. So it can grow only if pressure inside is equal a little bit more than outside atmospheric, which is 1 atmosphere. 10 to 5 Pascal, 100 kilopascal. And then air bubbles can start growing, and this is what we call boiling. There is Clausius-Clapeyron relationship. Ever heard about it?
Probably.
Probably, yeah, I guess Todor has heard, because it was you were with students probably somewhere there.
No.
No,
I just don't remember it.
Very good. Now, Toma, what about you? Do you remember what is a Clausius-Clapeyron relationship?
I don't think I have heard that before. If you've been writing on the board, I don't see anything about.
No, not yet. So maybe
okay.
I start, first I was just discussing and then I start writing. Right
Okay.
now, what we have on whiteboard is just only written rain formation in warm clouds. Later I write everything on the whiteboard as well, but right now we are just discussing.
Okay.
So Clausius-Clapeyron equation, what is it? Relates what to what?
Pressure, saturation pressure, and temperature. Right.
Well, actually, it's more generic. Clausius-Clapeyron, but it's in particular it can describe that as well. So it relates latent heat of phase transition to the pressure at the pressure derivative of critical pressure over temperature. Critical pressure is at which phase transition happens, but this is a function of temperature. So dB critical over dt, it relates to the latent heat of phase transition, and molar mass and things like that. But in particular, in the case of gases, it reduces, that has also another name, but I don't remember the name of the formula, which expresses the saturation pressure as a function of temperature. Basically, it's exponential law, and so it grows very fast until a triple point is reached, but let us not skip that triple point discussion right now. Saturation pressure is very fast-growing function, and so if we call saturation pressure at normal temperatures is not that big. So actually, there is only a small fraction of total mass in the form of water in here. Now, where did I want to go? So we concluded that dew point is when mist starts forming, and so we also concluded that clouds are mist, actually, small water droplets, and now how can in the atmosphere cool down to form mist in the clouds? Now, look, if you think about it, you can have mist during night or early morning because air cools down due to heat radiation. But that isn't happening in the upper layers of the atmosphere where clouds are forming. there is no not much heat radiation over there. So why is air cooling down below dew point?
Is it gravity?
Gravity. In which way gravity does it?
Reduce the energy when to climb all the way up, you need to fight against the potential energy?
Not exactly. So it's buoyancy force can bring it up, yes. But there is no buoyancy force itself does not cause any temperature loss. So what is making temperature loss over there for EMSs? Tooma, maybe you can suggest. Now, one keyword is missing, then our picture is closed.
Like, what the question is, why do we see, what causes the dew point in the upper atmosphere?
Yeah, why in those layers where these altitudes where clouds are forming, obviously, temperature falls below dew point. Why does it do that? And in some places it falls, there are clouds, in other places it doesn't fall below, there are no clouds. So if you have those partially cloudy weather, then clouds are not everywhere, only in some places.
Because it's of humidity. It's why clouds form usually over the ocean and then disappear when they go over land.
It is related, but not quite yet, not exactly that, but it is related indeed. Maybe you have noticed when you flew by plane over sea and over islands and continent, you often can see that above the sea, there are no clouds. But each island has its own small cloud on top of it, and a continent as well. Why is it like that? And another thing, if you are in mountains, then you might have noticed that sometimes clouds are stuck to mountains. Each mountain has its own cloud around it.
And it's not radiation.
It is not radiation, because these mists are close to Earth's surface. We can also discuss why it is not radiation, but first let us try to figure out. Oh, well, I can tell you why not radiation. So, you know, second law of thermodynamics? No? Otto surely knows. What is second law of thermodynamics?
Not by name.
Second law of thermodynamics. Usually people know it by name. But Otto obviously forgot it because it was already so many years ago. Tooma, what about you? Do you remember what is second law of thermodynamics? Tudor has excuse because he was doing master and undergraduate in math. So he has excuse of not knowing. Second law,
Yeah, I usually forget the order. Is it related to? Is it the one related to entropy?
Yes.
Okay.
It's all related to entropy. That entropy can go only in closed systems. Entropy can only grow, but it has equivalent formulations, and one of them tells us that heat cannot go from heat will flow only from higher temperature bodies to lower temperature bodies, and from there we can actually show that if something absorbs, it must also radiate in the equal degree. So in particular, we have if we have a black body or gray body, then the so-called emissivity equal to absorbance. So as as large fraction as the body radiates from the black body radiation, the same fraction is absorbed from the incoming white light. If it were not the case,
In
then we can build a system where entropy will grow, because in that case we can make it so that we just use that medium which, let us say, absorb more than radiates, and then make it little cooler than the other one, higher temperature, and then just radiation will start flowing towards that. So by contradiction, we can conclude that anything which is absorbed by a certain fraction as compared to black body must radiate also at the same fraction. And that means that if air is transparent, it cannot absorb. It doesn't absorb because it's transparent, but it means also it cannot radiate. Things are different for actually infrared. So we know that CO2, for instance, or water vapors actually absorb infrared radiation. So they also can radiate in infrared range a little bit. But clean air without CO2 or H2O, the radiation is very, very small. And even if there is some water pressure, it's still radiation is not that big, again, because it is transparent mostly. Only in certain wavelengths it absorbs. And so because of that, air mostly loses heat with contact with cool surfaces. So you know that during cold nights, Earth's surface can be usually is colder than air, the surrounding air. So temperature, the thermometer shows, let us say, at 1 meter height or 2 meter height, shows plus 1 degree, but that already ice is forming on the surface of Earth. So water is also very opaque in infrared, so it also radiates very, very much, actually, water surface. So ice starts already forming on water surface, but even so, temperature is air temperature is more than 0 degrees. And so because of that, mist is usually formed or close to Earth's surface, because it loses contact, air loses heat while being in contact with ground, which is losing heat by radiation. That's how it happens. But up in mountains, there is no ground is still very far, because clouds are still not they are very big, and even so, at the contacts there could be some heat radiation. Overall, in overall picture, is very insignificant, because we have large air masses over there. So now again we are back to square one, and why we have a temperature in air falling below dew point.
Is it because the wind is stronger?
It's related to wind, but not quite. I'm missing one good keyword. If someone tells me good keywords, then we can move on. If you cannot, eventually I'll tell you, but.
I was thinking of radius of rotation, or.
No. Toma, let us see if Toma cannot say, then I just tell you.
So we're still wondering why we get cloud formation in specific locations. Okay.
Why temperature falls below dew point in clouds? And you have been given quite a bit, many hints already that clouds are forming first on Earth's surface. They are forming near mountains.
Yeah. So is it that the mist?
What is that? Yeah.
Does the mist raise into clouds, or what's the idea?
No. So what is there in mountains and on the Earth's surface as compared to sea?
We already talked about humidity, temperature gradient.
Well, Let us say, let's not talk that much about humidity right now, because what I understood is that as long as we have some humidity near, if it is cooling down, we have mist, and clouds are mist. So let us forget about humidity and let us ask why air temperature falls below dew point.
I mean, I was under the impression that in the upper atmosphere, it's already quite cold, like below freezing.
Yeah, that's good point. And why is exactly that? That's very good point. So in upper atmosphere, it's very cold. So if you go by plane, it can be very, very cold, -50 maybe. So why is that? And Otto surely knows, because that was part of our thermodynamics course, but but it was so long time ago.
Yeah, so sorry, it's been like 9 years. It's been 9 years since I took thermodynamics.
Yeah, exactly.
Their pressure is also lower.
All right, let me tell you a keyword, adiabatic atmosphere. Does it sound familiar to you?
Yeah.
So what is adiabatic atmosphere? Is an atmosphere where air is moving up and down. And so when it moves up, pressure goes down, because we have like hydrostatic column pressure, there is less.
So it is gravity. So it is gravity.
Yeah, but not directly, not directly. And so there is a smaller, why I wanted to hear about adiabatic law. That's what keyword adiabatic I wanted to hear.
But in the end, the pressure difference is caused by
pressure
gravity.
difference is because of gravity. Yeah, pressure difference is because of gravity. But now the key point is that air masses are somewhere rising. So adiabatic atmosphere happens when you have a nice weather. Sun shines at least some places, or just you have wind. And when wind, you have turbulence. With wind, you have turbulence. Somewhere air masses are going up, but somewhere they are going down. Now, at every altitude, still pressure is more or less the same, but air masses move up and down, so air is usually very well mixed. This means also that the temperature, now turbulence and mixing, right? Temperature is also very well mixed. At the same height, the temperature is always more or less the same. And now a adiabatic atmosphere is such an atmosphere that when one parcel of air rises from bottom to top, it expands adiabatically because pressure goes down, yeah? And as it rises, it obtains the same density as the surrounding air mass is the same altitude. So it will be in equilibrium. Otherwise, there would be buoyancy force and some it will still push up. So adiabatic atmosphere is when air parcels goes up and expands adiabatically, it obtains the same temperature and same density as surrounding air at the same altitude. And then you can derive it, and you can obtain a very nice law that temperature goes down linearly, according to a linear law. And that we derived actually during our thermodynamics course. That's in that linear law. And now you can easily understand that in those places where air masses are going up, you have clouds, because they go up and expand adiabatically and cool down. And because it's well mixed everywhere, you have the same temperature at the same altitude. And it's also the same humidity because it's well mixed. And now, so everywhere where the rising air masses, where there are rising air masses at the critical altitude, where saturation pressure becomes equal to relative humidity becomes 100%, meaning that dew point is reached. That is a lower boundary of clouds. And because this happens for everywhere at the same height, because water air is very well mixed, so we have very flat bottom. And now let us start writing down what we discussed. Now, just because we have a lot of text to write, let us do it typing in here in the screen. Now, where do we start? mis dew point. Dew point. My keyboard is let me is not should be short. I'm switched to wrong keyboard, and now I'm trying to switch it back, but because that stupid
Try Windows key and D.
Windows key and
D.
B.
There.
Ah,
There you are.
okay. Dew point.
And now click on it again. Yeah.
Relative humidity 100%. Idest saturation pressure, vapor pressure equals to saturation pressure. Okay, so when temperature falls below dew point, dew is formed on grass, and mist is formed. Now, same happens in clouds. Okay, let's finish here. That this happens close to ground. Because cools down when in contact with cold ground, and the ground that loses heat by radiation. Okay, that's what we discussed, right? The same happens in clouds where EM masses go up and cool adiabatically. Now, in mixed atmosphere, absolute humidity, density of water vapors, is everywhere the same. So the dew point is always also same everywhere. Also the same everywhere. And now in well-mixed atmosphere, there is rising air masses have the same density and temperature as the and well, basically, and hence well, first in atmosphere, let us start actually from saying that the pressure It's actually even not in severe mixed atmosphere, but in anyway, always in atmosphere. In atmosphere, at least in close distances. In large distances, you have cyclones and anticyclones, but in close distances, the pressure is the same. The pressure is the same at the same altitude. Because if it were not the same, just pressure would push the air masses to sidewards because mechanical, because there is mechanical quasi-equilibrium. Now, in well-mixed atmosphere have the same density of from the ideal gas law, hence the same temperature at the same altitude. And now, hence, the dew point, the temperature falls below the dew point at everywhere at the same altitude. Does it make sense? Is it enough now? Is it clear enough? A lot of text, but I think it mostly covered what we discussed.
So why do clouds exist at different heights then?
That's also a good question. But because atmosphere actually is not necessarily homogeneous through the whole height. Normally, it depends on the weather. So if you have nice sunny day, then normally you have actually a well-mixed and adiabatic atmosphere up to the quite high altitudes. So 10, 15 kilometers, close to equator, even higher, even 20 kilometers. Now, and then there you wouldn't have clouds at different altitudes, everywhere the same altitude. But above that, there are different, like stratosphere and things like that. And then there you can have a different air masses that totally different, unrelated. It's a different humidity and it's not mixed. So you can have different another layer of clouds higher up because that's not part of the adiabatic atmosphere anymore. And now, depending on weather, this can come also down from the stratosphere to a little low altitudes. And now, speaking why are clouds around mountains? Now, can you tell me why clouds are formed and stuck to mountain tops? If you have single, like very high mountains, sometimes there are clouds stuck to it. In particular, close to sea, you can have that quite often.
Constant source of hot air?
Yeah, kind of, and it also directs air masses up along the slope. And islands and continents, the same things, that the sun heats ground, and this makes air parcels rising up, and then vertical upwards motion gives rise to cloud. Where air masses go down, there are no clouds, and where air masses go up, there are clouds. Okay.
So if you see a cloud that you notice is just unusually high up, what does that mean?
It's dry. Humidity is low. Then because dew point is lower, it needs to go down more, and so that happens at the high altitudes.
Why can humidity be lower?
It depends where the emissions come. If they come from sea, where a lot of evaporation happens over a warm sea, where a lot of evaporation happens, then yeah, humidity is higher. Or meanwhile,
For
if
the same spot,
ah,
for the same spot, why can you have lower humidity than at different times?
yeah, EMSs are coming from different places. Normally, EMSs are big. They are. Think how thick the atmospheric EMSs that move are. So then, as I said, atmosphere is on order of like 10 or 20 kilometers. And not all that layer is necessarily moving horizontally, but quite a big, significant part of it. And so in order to increase humidity of those big masses, a lot of time is needed. It doesn't happen just if it moves a little small piece of land or water that it can obtain enough humidity to increase overall vapor density in there. So it needs a lot of time spending on about water surface and like mixing turbulent motion up and down to obtain humidity, a grow humidity needed for cloud formation.
So then,
Also, if during summer times, you might have noticed that in the morning a cloud is clean. By afternoon, clouds start forming. Why is that?
the sky is clean,
Yeah, clear.
right?
So why is that? In the mornings, no clouds, afternoon clouds.
You needed new hot parcels to be generated, or
Well, sun is heating ground. And now ground, if there is ground is wet, maybe there was rain yesterday or overall hasn't dried much up yet. Quite a bit was rain recently. It's humid and evaporates. And during the morning time until noon, enough humidity gases into air so that now there is enough for it to and all certain layer gets into vertical motion. So during nighttime, you might have you definitely have upwards motion stopping because upwards motion is propelled by heating, by buoyancy force. Now, during night, the opposite happens. Ground layers cool down because of heat radiation. What happens is called so-called inversion. So which means that unlike in normal situation where higher up air temperature is lower than the other way around, ground is cooler than up, and this is stable stratification, which means that not easily can EMSs start moving up. And so now we need some time to warm up the lower layers of air so that it starts moving up on the one hand. On the other hand, it needs to collect also enough humidity from the ground. And then clouds are forming, and maybe by evening there is even rain going. And then rain dries again up the humidity from here, and then next morning again it is clear sky. Okay.
so why does rain happen all in a big chunk rather than a little bit here, a little bit there? Why is there a tipping point where the rain starts and then it just fully goes?
Yeah, that was actually the very topic of today's lecture. Let us not rush, and the rain formation I still haven't touched. We just first to start discuss cloud formation, but not rain formation. Now, is it should I write something what I said here, or is it enough what I have on the screen right now? What is the feeling?
Quick question. So just to be clear, when we are talking about altitude, Do we mean altitude above sea level or above the ground locally?
Doesn't matter, just the same reference level we need to talk about. So we can speak about from sea level, for instance. Because if you speak about dew point and things like that, these happen. Yes, okay. We shouldn't take the same altitude from ground. We need to take the same altitude from sea level because suppose you have mountains somewhere and like a valley somewhere nearby, then air density is still function of only altitude from the sea level, not from the ground level, right? So what matters is air density, air pressure, and it is also smaller in mountains. So if clouds start forming at the same altitude from the sea level.
Ah, okay. Thank you.
Mhm. Now, once again, is this text enough, or should I write something additionally about this at all? And if something, then what?
I
Probably,
think it's,
yeah.
Enough.
Enough, yeah, because writing everything would be useful, but would take too much time probably. So it's not those are not so difficult concepts. So I hope you more or less has understood and remember it more or less. See how it goes, and these are some key points what are written here. Okay, so now we know why we have lower. Can you hear me, Toma, now?
Yes, thank you.
Yeah, but connection was lost, right? It seemed to me at least.
Yeah, completely. Right after
Yeah.
you were asking
Okay, so where was I? Yeah, clouds are basically big vortices where air moves at the center of clouds, air mass moves up, and inside sideways it moves down. So a vortex which has vorticity is like walks a ring along cloud. And maybe I should draw it. Maybe I should draw it. Oh, cloud. Oh, air mass is going up. And here is the cloud. So, and yeah, upper boundaries just depends how high is air flow carries the mist. And then at the sides, we have descending air masses, and these are dry, and there is clean sky there. And if you happen to be on sea, sailing perhaps, then you would need to know exactly that clouds are such kind of vortices because you want to catch winds, and this happens close to the cloud boundaries. So sailors usually know quite well that clouds are around clouds are winds. Okay. But now let us move to what we wanted to discuss at the beginning, and that is rain formation. Now we have mist, but mist is not rain. Now the water droplets needs to grow big enough to start falling. Last time I spoke about Stokes time. Very light particles are moving together with the air masses. Now, first they need to grow mass to start separating for air mass, and then even more collect mass to start falling down. And now let me take another screen. Not many screens today. Now, so rain formation. Now mist. Now these are mist are micron-sized droplets. Now, guys, have you following air quality? You know, but you should. Do you know that normally many more leaves are lost because of so-called PM10, particulate matter 10 micron-sized particles, as compared to, let us say, car accidents? What? Yes. Because of poor air quality, there are very many leaves lost, actually. These are chronic illnesses and all that. They are to begin with, they are quite often caused by those particulate matter. But then again, it makes more, if you already have it, it makes it more acute. So it is good idea actually to follow. Guys here in Estonia, I have some very good news for you. Estonia is one of the cleanest here actually throughout the world. Even cleaner is if you go to Finland, maybe in Lapland there is even cleaner. But Estonia is luckily one of the best places. Europe itself is not that bad. So Central Europe is normally quite okay, but there are some troublesome regions like Poland, maybe some Poland and industrial regions where there is like sources of particulate matter, and now it depends where the wind comes. There are sites which make forecasts of that particulate matter. I think PM 2.5. PM 2.5. That is particulate matter. Matter 2.5 micrometers. There are also, if you look at those air quality measures, there are also PM1, PM10. I think normally, like what mostly looked at is PM 2.5. PM10. And this is one thing that it is bad for your health. But then again, you always have some, more or less, but you always have some. And these are, we speak about order of magnitude of 1 micrometer. And that's where droplets start forming around those. These are centered. Okay, bad for health. You can just Google and how many health leaves are lost, and you can you will be surprised how many actually by country you can look. And these are centers of conversations. Centers of conversation.
So is it just the size that makes it bad, or is it some?
Yeah, the
what it
size is,
usually
the size is important, actually. If they stuck to your lungs, and don't ask me about detail because it's already into medicine more, but actually size is what makes it bad. So 1 micrometer is not considered that bad, I think, and probably PM10 not also not that. Maybe it gets the, so if it's bigger, it's just it gets out more easily if it gets stuck and then gets out, but maybe the 2.5. Just speculating, don't know. But what I know is that so the medical statistics tells that a lot of lives are lost. But for our point of view, we are interested in that they are center of conversation, and droplets start at around 1 micrometer size. And droplets start from radius around 1 micrometer. No, that was not micro. And then grows by diffusion. Grows by diffusion down to up to something like 20 plus micrometers. And then they start colliding. And now until that point, Stokes time. You remember what was Stokes time? How long time it will take for particle to obtain the speed of the fluid? It's very small. It's so small that we can neglect the inertia. Neglect inertia. And now from that, from 20 micrometers, from 20 to 60 micrometers, that is basically what is called a bottleneck. The bottleneck now was 60 micrometers. The bottleneck. Bottleneck. Now, what is a bottleneck? Diffusion growth is very slow and won't happen anymore normally, but they are too small to start colliding. Diffusion very slow, but collisions still don't happen. But inertia still too small to initiate collisions. What is the problem? First is that Stokes time is small, but that's not all. Even Stokes time is small, it could give rise to certain detachment of particles from the flow. But the problem is that all droplets in the same volume are more or less have the same size. Now all droplets in a volume have nearly the same mass of size. And this means that even if they are detaching from the flow, they detach all in the same way. They detach from the flow in the same way. Which means that there is no the same velocity. They have the same velocity and cannot collide. So I need to write that collision is needed for a droplet close. Or is it obvious? That is needed for a droplet cross. That is needed for droplet merger and cross. Needed for droplet merger and cross. And that is a bottleneck. Now, what is it? It's called bottleneck because it is very slow. So estimates, if you do estimates, you would expect rain initiation when you have a cloud form and rain starts falling down. You would need to have something like 10 hours, simple estimate. But reality is different. In reality, it happens in half an hour or 1 hour at most. So we have a mismatch by 1 order of magnitude. And that's why, like the theoreticians call it bottleneck, it should be very slow, but in reality it's not. And so that's like a big challenge to explain. And it's still not like unanimous understanding why it is like that. Now, more or less clear what is about bottleneck and why it is important. Why it is important? Well, there are plenty of places where you want rain, and then if you understand rain initiation, it will help like you if you want to create rain, for instance, things like that.
Molecular particle would move randomly in Brownian motion.
Yeah.
And the larger it becomes, the smaller the amplitude of
yes,
this movement.
Yes, and they are big enough so that the Brownian motion is negligible.
Completely.
Yep.
Even compared to the distance between two droplets.
And the distance between them is still luckily quite big because you remember they are all around these particular matter particles. There are no more than there were initial condensation centers. There are exactly as many droplets as there were concentration centers. Luckily, in most cases, there are not too many.
Why do you say luckily?
Because I mentioned to you before that it is a health hazard. Okay.
So our industrial activities are going to make rain fall faster?
Yeah, that's also true, yep. Well, at least faster, maybe. Maybe faster, but maybe not, who knows, because if say, okay, there are more droplets, but we have still the same humidity. It is not necessarily good news if you have a lot of particles, particular matter. If you have a small number of particular matter, then you have less mixed droplets, but still the same amount of humidity, which means that each of the droplets is bigger. And remember that we need a mass to start the collisions. So actually, it might be other way around, that actually, if you have too many particulate matter particles, that is not helpful.
So then let me ask the other way. The water in the clouds that is not yet in a droplet would have somewhat of a Brownian motion attached to it.
Yeah, and that's, I mentioned, that is called diffusion.
Right.
I mentioned before that from 1 to 20 micrometers, droplets go by diffusion, and that is Brownian motion of water molecules.
All right, I'll go
And
for
that we
another.
are going to do some math here as well. With that, we are going to do some math, but yeah.
So I'll give it another shot. If the wind direction changes, then it will take longer for the droplet, which has a proper mass, to go with the speed of the wind, of the new wind, than for the water in the rest of the atmosphere. And we do not account for that, I imagine, when we compute the fusion.
Well, when droplets already fall down, that's good, and everything will get
No,
together.
before they fall down, when the bottleneck size.
Wind, you have in the clouds, you have always wind turbulent motion. That's always there, and actually that is definitely something which helps droplet formation, that overcomes that bottleneck. And one of the explanations is exactly so you can estimate that 10 hours estimate that is actually already taking into account air motion, so that you have a turbulent motion.
Yeah.
And then you have, you remember that was Kolmogorov scale. Kolmogorov scale has the smallest velocity. Velocity is proportional to scale to the power of 1/3. But if you take acceleration, then the Kolmogorov scale has the largest acceleration. We can do that math here as well. So Kolmogorov scale lambda, and then velocity at lambda, and now actually Kolmogorov turbulence. It means that velocity at scale A is proportional to A to the power of 1/3. Now, time scale is tau associated with scale A is estimated as scale divided by velocity at that scale. And then that will be now scale to the power of, did I write it now correctly? This is A to the power of 2/3, proportional to A to the power of 2/3. Am I right? If I divide A to the power of 1/3, 2/3 remain, right? And now that is time scale. Now acceleration. Acceleration at the scale A is proportional to V at scale A divided by rotation time at scale A. And then that is now A to 1/3 divided by A to 2/3, which A to minus 1/3. Which means that the smaller vortex you have, the larger acceleration it exhibits. Which means that if you go to a large plane, you have less turbulence than when you go to small plane. Shaking you less in large plane. In that Airbus 3800, maybe. It's more convenient to fly than some small one. Because if your plane goes, it feels only the vortices turbulence at the size of the wings. Because it's average. If it's a smaller vortex, it is averaged over the wing. If you have small wings, it averages over a smaller area, and so it means that you feel acceleration of a smaller scale vortices, which is bigger. Okay. Now, so if we speak about detachment of the particle from the airflow, which is needed for collisions, that need to have larger acceleration of air masses, because that is a force of inertia which is detaching them. Okay, so the detachment of droplets. Attachment of droplets. Caused by force of inertia. Inertia m times a, but a is proportional to the scale to -1/3. So the lambda scale vortices have the strongest effect. And so now, yeah, if we take account what is the turbulence and what is the Kolmogorov scale, something like 1 to 0.1 millimeters maybe in air, maybe lambda maybe around 0.1 millimeter order of magnitude. So that's where the detachment happens. And but still, yeah, if you take this into account, what is the acceleration at that scale, you are still at that 10 hours of radiation time. And now, one of the explanations, one which actually believed to explain part of the bottleneck, is so-called exactly that so-called sling effect. So detachment of particles is a sling effect. This so-called sling effect, and this is supposed to explain, but sling effects are not of those Kolmogorov scale vortices, but due to intermittency, some of the Kolmogorov scale vortices are stronger, and they can even longer, a little to lower scales. So dissipation stops the Kolmogorov cascade, but if some vortices are stronger than the others, they can survive at a smaller scale. So if you have, due to intermittency, some vortices are very strong, so they give correspondingly larger acceleration. Intermittency, this means that some vortices are stronger and smaller. And smaller explain some of the maybe something like 40%. Okay, 40% of the bottleneck. Still some is missing, but that is some explanation. Yeah. The other have actually, well, to explain the bottleneck, you can have two things. One is detachment. The other is make droplets in the same volume, wider spectrum of sizes. So two explanations, so two ways to resolve. Solve the bottleneck. Nice sling. Effect, which means a detachment, right? I wrote it before. Probably you won't be able to understand what I wrote here. That sling effect, maybe you can understand, but sling definitely not. Second is different wide spectrum of droplet sizes. In the same volume. Remember, I said that the problem is that they are all have the same size because they grow in the same environment, and if they were to have different sizes, then that would explain the bottleneck. And now there are different theories. I have one of my own, not very actually completed. It's like a good idea, but I applied for grant, but then I didn't get it, and then it's like one of my unfinished works. So my idea is that the droplet size spectrum can grow because droplets have very different histories. Some particle due to mixing. You remember we have. That some places we have mature fronts of temperature, let us say, when they're very different places, fluid parcels are brought together with very different temperatures. And the same way you can bring together droplets from different parts where they have very different histories, and because of that, very different sizes as well. That is my own explanation, but yes, it is still like one of important and not quite enough understood things in turbulence, and quite important at that. Now, I am going to do also now some maths, but let me give you some opportunity to ask. We are mostly done with that rainfall initiation thing, because first you more or less understand how it happens, and then you understand that there is a theoretical challenge still to solve here. Now, any questions at this point?
Yeah, you're talking about vortices.
Yeah.
Why is that important for our droplet?
A Kolmogorov turbulence. We have like this. We have vortices of different sizes, big vortex.
Sure, but why does it matter?
I just explained that we need to accelerate particles, droplets, for them to detach from the airflow so that they can start colliding. If they move together with airflow, they will never collide.
Why would they move together with airflow?
Because they are very light. They grow, they are only mist-sized particles, like 10, 20 micrometers. They are so light that they move perfectly together with air mass. They won't settle down, they won't move anywhere.
So when you have a vortex, as you said, why would they go with the same speed?
Well, if you have vortices, then, okay, let us see. It's kind of actually a good question what you said, what you asked, but let us take droplet, another droplet. Let us say we have gravity down here, okay? Now we have small Stokes time, very large, small radius, relatively big Stokes force, drag force, Stokes drag. Small particles, small radius, large Stokes drag. Relatively large Stokes drag. They settle down when gravity very slowly, but still they do settle down a little. But those particles settle down at the same speed. Here is one droplet, here is another. They move together down, settle down with the same speed because they have the same mass, the same radius, same Stokes drag, same gravity force. The ratio of them defines the speed. They settle down with the same speed. They will not collide. Okay. Now, let us take a vortex. First thing is that the acceleration of the caused by the smallest vortices. Let us look back here again. So that was proportional to A to -1/3, which means that small vortices can have very big acceleration, more than g. So force of inertia can be quite a bit bigger than the gravity force.
But for
That
now,
is one thing. That's only
Yeah.
half of the thing.
but this is just for the small particles in the, just for the air for now,
Yeah.
right?
Yeah.
Yeah.
Yeah. And so this one thing is that they are the force of inertia is bigger than G. But the more importantly, even, is that here we have one vortex like that. Vortex. And now here is no vortex. Here is somewhere separatrix. Okay. So there is maybe vortex something like that here, or well, who knows, the different direction. So now we have a droplet here. That droplet gets detached and moves to here. And now, because that droplet and that droplet have different forces of inertia. So that guy here is pushed here, force of inertia. That guy is pushed here, force of inertia. Centrifugal force, basically. They are pushed in the same direction, and they now can collide because of that.
But for them to have a force of inertia, they needed to have gone with the vortex speed to begin with.
Ah,
For them to have this force of inertia, they needed to have gone with the vortex speed to begin with.
yes, they are moved together with the vortex speed because they are very light and they move together with the fluid. They are so light that they move together with the fluid perfectly. I said that they had so small droplets, they move almost perfectly with the fluid.
But they move perfectly with the fluid in a vortex because the fluid is pushing them, right?
Drag force is carrying, Stokes drag is carrying them.
So they have constant contact with other bits of water.
Sorry?
So they have constant contact with other bits of water. Other bits of water in the atmosphere, right? Because they are actively getting pushed and moved around by the vortex.
Yeah,
So it's more than Brownian motion
no.
that is diffusing into them.
No. So yeah, okay. There is no Brownian motion. So anyways, a droplet is still too big to have Brownian motion.
No, not the droplets Brownian motion, the diffusivity. So the atmosphere's Brownian motion. The air's Brownian
Okay, we haven't done that. We are going to do, but that has no effect. So that the diffusion from the water molecules, water vapor molecules, they just grows of all the particles in the same way because humidity is the same in every way. That altitude. Remember, I started with saying that the vapor pressure is the same at the same altitude, meaning that this vortex and that vortex have exactly the same water vapor pressure. Which means that the both particles will get the same growth by diffusion.
Okay.
And the only thing which can bring them together is having some different forces of inertia. Now you can also recall last lecture, previous week, when I discussed the inertial particles in turbulence, and there I showed that the very same force of inertia actually is completely compressible, which means that they start bringing particles together because it was like a force proportional to the gradient of pressure.
So
The velocity which is proportional to radius of pressure, which is completely compressible component of velocity, which starts which is causing gathering into patches. And yeah, this is sling effect. Actually, yeah, to be more precise, sling effect is not just force of inertia, but force of inertia pushing them through the separatrix. To have one vortex, and then particle moves here, and likewise the sling is pushed out. Okay, that's a sling effect.
So in that case, it's not moving together with the air.
I'm always saying that this is small. This is very small. So detachment is very small, and you need to have very strong vortices. Anomalies long vortices are stronger than normally to have this working. So that detachment is very small, and normally is not able to explain the bottleneck. Normally, yes, it is there, but it's so slow that you would need 10 hours.
Okay.
No, if you take just a Kolmogorov scale. So what is that Kolmogorov scale are too weak to explain that. you need to have include intermittency and include some, say, most violent small vortices which have strongest link effect, which can make it. Okay.
Okay. So you don't really mean force of inertia there, right? Because force of inertia only makes sense in a rotating frame.
No, exactly what I say what I mean. You can you move together with the ear parcel. Just the reference frame of this parcel here. That move with acceleration, and that frame in that frame you have force of inertia.
In the rotating frame. Yeah.
In frame, and not necessarily rotating. You can also go to rotating frame. I just prefer to go frame which moves together with a parcel without maybe rotation. So force of inertia is acceleration multiplied by mass. And that's pushing it from away from our frame. Our frame is together with the fluid, with airflow. Air speed is 0. Now, particle speed is not because it has force of inertia, which is pushing it. How is it?
Wrong.
What is wrong?
Force of inertia is a false force that appears when you rotate a frame.
And now, force of inertia, you're confusing now with centrifugal force. That is centrifugal force which you're speaking about. Force of inertia is in a frame which moves with acceleration, not necessarily rotating.
Oh.
Yeah, you're confusing two things. Force of inertia and centrifugal force. You speak about centrifugal force. I'm speaking about force of inertia. Although you could here also speak about the centrifugal frame if you go to a rotating frame where like frame where the axis rotates like that. In that frame you would have centrifugal force.
Okay.
But there would have also Coriolis force and all things. So I prefer to use only force of inertia with a non-rotating frame. Tom, how are you? All fine?
Thank you.
Now, daughter, are you happy? Almost there?
Almost. What is your frame here?
I chose that yellow circle. This is a frame which moves together with the air passer. And it moves with acceleration because that's how air passers move in a vortex.
So why is the force of inertia not the same for the other particle?
Because that moves into that has different frame. That frame moves like that. Because the two vortices have different velocities. The two frames have different velocities. The air parcels have different velocities.
So you have two systems of reference in the same drawing?
Yeah, I have two reference frames, yeah. Well, I care about detachment. And I use each of those frames to figure out how it is detached from the airflow.
Okay.
If they were not detached, they would just move together with fluid and never collide.
Yeah.
All right, can we move on? Okay. Now, now going to spectrum growth. And so I said my own explanation is different properties have different histories, but let us before that let us leave it as that because this is not published work and all that. But let us just elaborate a little bit about point 2. Let us elaborate on how exactly they have the same size. And let us do some math as well. Particle diffusive growth. The last thing about these droplets now is a diffusive growth of droplets. Now, droplet has some radius, I said around 10 micrometers, from 1 to 20 micrometers, something like that. Radius R. Now, radius R is the rate of the droplet. Now, at the surface of the droplet, water and vapor pressure is at equilibrium because they are at immediate contact. Now, okay. Here, pressure vapors equals to pressure of saturated vapors. Meaning that relative humidity, okay, so let us make it relative humidity, R sub H, is 100%. Because they are just in contact at the surface. But story is different here. Here we have some, if we have a droplet close, we have some oversaturation. So we have some delta P. Delta P is defined now as PV minus P saturation. This is called oversaturation. Oversaturation. And we can, maybe it's more convenient for us to work in terms of a number density. Delta N equals number density of vapors minus number density of saturated vapors. And a number density. Number density. The number again is not very readable. Because of the time lag, it's very what I am writing is getting even worse. So I need to write very slowly so that it will more or less make sense. Number density: how many particles in per volume, per unit volume. Now these are diffusing. So now we consider diffusion problem. 3D diffusion problem. We have a distance from the droplet. Okay, let us actually make R capital. The radius of the droplet does make R capital. Because R small will be distance from the center of the droplet. Here we have R capital. This is that droplet radius. And now oversaturation delta N. That is 0 at water here. And it has some infinite value that delta N at infinity. And now it needs to go from here to there. Go like that. Okay? Now, what is the shape here? Can anyone tell me? Any idea what it might be as a function? How the oversaturation in the air around droplet depends on distance from the center of the droplet. At the surface of the droplet, oversaturation is 0. At very large distances, it's certain delta N, which is oversaturation of these air parcels here and now. And what is the shape? Any suggestion?
I can tell you what delta N of infinity is.
That's just given. Delta N at infinity is this thing here. This depends on the V and then SV. So this is just some number. But what is the shape of the curve? So what equation do we have? We have actually here now, because you wanted to have Brownian motion, here we have the water molecule diffuse by Brownian motion. So we have diffusion equation. We have a dN over dt equals molecular diffusivity. Let us denote it by kappa. Could be also d, but let us right now be kappa and a Laplacian of n. That is the equation. Everyone happy with that? Makes sense?
Yeah.
Makes. Of course it does make sense. Now, because the distances are very small, we speak about micrometers. Now, the diffusion speed, by the way, do you have idea how fast is diffusion at, let us say, 1 micro or 10 micrometers? Do you have any idea? It's sort of long. Do you have some reference number? I do have one. Like if you have 1 centimeter, then for heat diffusion, but heat diffusion are basically same as more or less like air molecule diffusions, the same rate happens. The heat diffusion is such that to 1 centimeter, it happens around 1 second. 1 centimeter, 1 second is diffusion. Okay? Now, diffusion fast.
So
what-
you marked it as centimeters a second, but if that's the Laplacian, don't we need centimeters squared per second?
Wait. I'm speaking, you didn't quite understand what I'm speaking about. I'm speaking about how long does it take for heat to diffuse from here, certain point to distance at 1 centimeter away. Or let us say, if you have some process with gas, with air, and you want to know if it is either thermal or it is adiabatic. If you can neglect heat transport, then it's adiabatic. But on the other hand, if it is heat transport is big, then the air temperature is the same as the surrounding, and it is isothermal. So it's very important to know at which speeds heat exchange takes place. So if you take a piston, like a pump, a bike pump, and it has maybe a radius of 2 centimeters. Then now how it time scales with the distance, it was squared, right? So if you take 2 times bigger, time goes 4 times bigger. So 2 centimeter radius of cylinder of a pump means that your heat exchange time is roughly speaking 4 seconds. So if you compress it faster, within half a second, it is adiabatic and it heats up. If you do it very slowly, it is isothermal because it takes the temperature of the wall of the pump. So that's why actually quite useful to know some reference number about diffusion here. And just it's very easy. 1 centimeter, 1 second is very easy to remember, right?
So what happens in 1 second for 1 second?
Heat transfers by diffusion to 1 centimeter 1 second in air under normal conditions. Atmospheric pressure, room temperature, then 1 centimeter in 1 second diffusion speed. Diffusion, you remember distance is square root of dt, estimated how far by diffusion particle can go. It is distance is square root of dt. Diffusion time, t, is estimated as distance squared divided by diffusivity. Now, 1 centimeter gives you 1 second, okay, of diffusion speed, diffusion time. It diffuses to 1 centimeter in 1 second. Meaning that if we have 10 micrometers, then what it would be? 10 micrometers is 100 times smaller, which takes squared, it is 0.1 milliseconds. 10 micrometers corresponds to 0.1 millisecond. Very fast. So at the radius of the droplet, the diffusion is very fast. What does it mean? It means that it takes equilibrium profile. It means that the time derivative part can be neglected. It is quasi-stationary profile formed. And it means that we have Laplacian n equal to 0. Okay. And now you need to solve this equation. Laplacian is 0 and we have spherical symmetry. What is the solution? Can you tell me? And now tell me in which lecture course during your previous studies you learned this solution. Toma, what is solution here? Do you know?
Could you explain the equation you wrote again with the Laplacian of n?
Ah, yeah. So we have yeah, actually, I have a small issue indeed. So confusing. Now I see actually you might really be in trouble because now I have denoted two things with the same symbol. I first introduced delta n, and then I introduced Laplacian of n, which has the same letter. Let me fix that thing first, and then I explain. And I also can pinpoint here on one mistake as well, actually not what I wanted. Not really mistake, but I wanted to have it for delta. So let us make this here different delta. Let us make it this delta, small Greek delta. And then let us make that here also small delta. And now, yeah, this equation, what I wrote for diffusion equation, is valid for n as well, but actually I wanted to write it for delta n, because it's valid for both n and delta n as well, because they are different by constant term nsv, which is constant. Now, yeah, what is this equation about? So this equation is diffusion equation, what I had at the beginning of our lectures. So we have a time derivative of something is diffusivity multiplied by Laplacian. So a diffusion equation. Let us recall. We had for temperature, for instance, we had dT over dt equals diffusivity and Laplacian of t. This is the very same equation. So for heat, it is like a Brownian motion for a temperature, basically. Any process with Brownian motion are described by diffusion equation. Now, and here we have for diffusion of water molecules, which means for concentration of water molecules n, we have diffusion equation, but I can subtract for constant term from left-hand side and right-hand side because they go away with derivatives either way. So I can also write equally valid for delta n, not n, but for delta n. Toma, did I answer your question?
Yes, I just wasn't clear what the left-hand side of that equation was.
Ah, yeah. This is time derivative. You know, again, sorry about not too well writing it, but let me write it a little bit. It was supposed to be d over dt of delta n. This, okay. And now the question is, what is the solution? Because we can drop from that the equation time derivative, because we said that the process diffusion is very fast at the scale of the droplets. Vapor particles, water molecules can diffuse to distance 10 micrometers in 0.1 milliseconds. So it is so fast that it is much smaller than the Kolmogorov timescale, And because of that, in our application, you can say that concentration delta n takes equilibrium value. We can neglect time derivative. So it's like a quasi equilibrium. And so we have Laplacian n equal to 0. Now the question is, what is the solution of this equation in spherical symmetry of this equation? Who can tell me the solution? Otto. Yeah.
Give it a guess.
No, please.
1 over r squared.
Almost there. Almost there, but a small mistake. Any better guesses?
Well, 1 minus r small r over r that bit squared.
Toma, what is your suggestion for the solution?
I mean, if the Laplacian,
4 pi.
Toma, yeah, please.
I was just saying, if the Laplacian of n is equal to 0, then I mean the n is not changing, or I guess delta n is not changing. It's constant, right?
So Laplacian of something equals 0. Have you met this before? And which course of physics was Laplacian of something 0?
I just mean in the equation you wrote for the rate of change.
Yeah, we have for electrostatic potential, don't
Yeah.
we have in vacuum?
We can do the whole analogy. That's
Yeah.
why I said 1 over, but it's the potential, so it's
It is
just 1 over.
potential, yeah. The donor suggested from electric field, but we speak about potential. So it's 1 divided by R. So it's n, now let me take next slide. So we have solution. We know from electrostatics, yeah, that a solution will be dn equals certain constant divided by r.
So that is, should there be only one solution or two solutions?
And yeah, there is the other solution as well, C1, and the other is trivial constant, C2. This is our solution.
Right.
And now we need to find C1 and C2 from our boundary conditions. And so dn at infinity equals, yeah, dn infinity, like that, okay? And then other thing is that dn at r equals to 0. Now, the first thing tells us that actually C2 equals to dn infinity. Doesn't it?
Yeah.
The second one means that C1 equals r times dn infinity. And here is our solution. dn equals r divided by r minus plus 1 and dn infinity. And now, we want to know how the droplets grow. Now we need to write a mass balance. So a droplet has, let us say, n sub L is number density in liquid phase. Number density of water molecules in liquid phase. Then we have how much it grows. 4 pi r square surface area multiplied by the growth of it, dr, this is the volume, and multiplied by n sub L, this gives how many molecules are condensing. During time dt, and that is equal to flux multiplied J as if the particle flux multiplied by 4 pi r square and dt. This gives how many particles are coming in, and the flux J is diffusivity kappa and multiplied by dn over dr gradient. Okay, so now 4 pi r square cancels out, and we obtain NL R square, sorry, not R square, dr equals, now derivative of n over r, we have solutions. This is going to be r over r square. This is going to be r over r square times kappa, but all that is to be taken as the surface of the droplet, because that's why the molecules, water molecules get attached to the droplet. So add r small equal to r capital and multiplied by dt still. This is our mass balance. And now from here, we can now finally obtain that r dr equals kappa divided by, the kappa was not too good, kappa divided by NL and dt. And now we can integrate this left hand side, okay, left hand side and right hand side to obtain that r square equals kappa divided by NL. We are missing here dn into infinity, sorry. Let us add it here. From the dn over dr, we are missing n at infinity, delta n at infinity, and delta n at infinity, dt. And because of that, r square equals kappa over NL, and integral of n at infinity dt. And that's important result now in that studies of Iranian initiation, which states that squared radius of a droplet grows as a time integral of oversaturation. Oh, sorry, here it needs to be dn infinity. No. Okay, that was the main thing what I wanted to derive today. We managed to do it by then. Are you okay with that? So it depends how big is a droplet, depends where it spent its time. How much oversaturation was that? Now is a question, what is at the end at infinity? And that thing actually here, a few words about that as well. So dn at infinity is formed by those things. If it moves up, it equals down, right? So so what is defines dn? What defines dn infinity? Now here moves up. Here parcel. Okay, so temperature goes down. So dn goes up because a dew point falls down, right? But that's not all, because now as we have growing dn, so it means that we have droplet growth. Droplet grows. So that drains away the N. This drains away the N. So it goes down again. So actually that is formed, so and this depletes, we have droplets here, and now this depletes vapor from the surroundings. We have not too densely droplets, but because there are hopefully not too many those condensation centers, but we still have some, and densely enough to deplete vapors from the surrounding. So there will be again now a kind of equilibrium. We have equilibrium between Dn is formed by an equilibrium of A d t dew point u over dt. So if a parcel goes up, dew points go down, and dew point is decreasing. So how negative is this temperature derivative? If it is negative, then we have this creates always more vapors. That increases Dn. And B draining to droplets. The more droplets we have them per volume, the more is drained away. So we can say that delta N is increased by this guy here and decreased by the density, number density of the droplets. That basically depends on those two. And then if air parcel moves down, then actually we have negative oversaturation, that goes also into that time integral. Okay, we have time integral for droplet radius. If we go here, okay, here is the time integral, then time can be also negative. And this needs to be taken because if we have water parcel moves down, then the droplets decrease in size. So if they move up, they increase. And now the thing is that normally you would think that all the particles in neighborhood have the same integral and hence have the same size. That's like the basic issue of the initiation because they have the same history, they have the same sizes. Droplet size spectrum is very narrow. You won't have collisions. And now you asked to find explanation how you can make the droplet size spectrum bigger. That's another side of the issue of rain initiation in warm clouds.
Here you say they have the same history, but when you absorb vapors in your trajectory, you're also absorbing vapors next to other droplets.
Yeah, but they are still very close. They are just still maybe hundreds of micrometers away. They are still very close, relatively speaking.
The vapors.
You have still we have different scales. So we have it drains away vapors in between different droplets. They are like hundreds of micrometers away, maybe even millimeters away. Droplets are millimeters away, let us say. Then we have diffusion drains away vapors in between these droplets. But they are still in the size of like parcel of millimeter size parcel, and then they still move together and won't collide. more or less?
Yeah, I just didn't buy the move together part yet.
No, move together because they are in the same fluid, and even if they don't move relative to each other, maybe they are in a different Kolmogorov vortices. As long as Stokes time is very small, they still won't collide because they just move because they are stuck to the fluid. They will not brought together by the fluid motion.
One thing we haven't discussed about turbulence at all is we've discussed the number, let's say, or the probability of a vortex being of a certain size. But we haven't discussed whether vortices of similar size are close to each other, whether they're covariant or not.
Normally not. Normally there is no reason to be close nearby. You remember that vortices are stretched and then folded like happens in the random motion, and that's happened with vortices. So they actually vortex filaments very long, and yeah, there is no normally turbulence is a set of vortex filaments. And they are different sizes. And yeah, that was actually now our time is basically up. Now, but we managed to finish the fluid droplets in cloud. It took us more than planned because we did it thoroughly and took our time just to introduce and everything. But I still hope it was useful. Toma, what about you?
Yes, I think so too. Could you go to the last page, please?
Oh yeah, last page. Yeah, okay. Last page.
Yeah, I just forgot to. I just didn't finish writing down something. Thank you.
Yeah. Yeah. So what is over there is that dn at infinity, the density of oversaturation in between the droplets, far away from the droplets, is formed by the balance of two processes. One is the decrease rate of dew point because particles move up. Oh, sorry, now you are wrong, completely wrong, not dew point. Temperature itself goes down, dew point remains the same. What I'm doing? This is a mistake. Temperature itself goes down, not dew point. Okay, so decrease rate of temperature is one process which is causing the increase in dn infinity. The other process is draining away the vapors to the droplets by diffusion, and this is counterbalance. And equilibrium of those defines what is exactly the value of dn at infinity. And the other process depends on how many droplets do we have per volume, what is the distance between the droplets. The smaller the distance, the more efficiently the drain away, the smaller will be the dn infinity. So smaller oversaturation, and there we have it. That actually, yes, the question is when if a lot of those particulate matter particles help rain formation or not, you can see that actually it doesn't help, because if you make the concentration big, then the oversaturation in the air parcels will be smaller because they are draining away more vapors, and so as droplets remain smaller. By the same, otherwise by the same turbulence levels, by the same decrease rate of temperature. Okay. Now, I said that we need to discuss also intermittency, but actually we spoke a little about already about intermittency. I said that multifractality, right? Something. Let me just say one thing. Because the sling effect also needs intermittency, which means that some vortices are more violent than others, and this everything comes down as what is called multiplicative cascade, which is slightly imbalanced. So let us say we have one vortex here as total energy E. Now this goes down into one vortex here, the vortex. It is stretched, and it becomes a smaller vortex, like in Kolmogorov balance scenario is. And another vortex, and one is slightly bigger than the other. So here is epsilon multiplied by, okay, let us say two-thirds, roughly speaking, it's not two-thirds, but let us say two-thirds, and epsilon multiplied by 1/3. Or maybe not two-thirds, but maybe 3/5 and 2/5 or whatever. The main thing is an imbalance. And then the same happens at the next level, again slight imbalance. And then at the end of the day, at the nth cascade, we have some vortices have energy epsilon multiplied by 2, 3/3, and to the power of n, and multiplied by 1/3 to the power of number of generations minus n. So how many times we take larger side and how many times we take smaller side. And if we have very many generations, if n is n capital is much bigger than 1, if we have a large number of generations, then actually these differences grow symmetrically, which means that some vortices are very small relative to the other ones, which are relatively speaking very big. And that's actually what intermittent is about, that some vortices are very strong. And this is a multiplicative cascade. Multiplicative cascade leads to multifractality and intermittency. The same, like different aspects of the same and intermittency. Mathematically, slightly different things, but related to each other. So both are describe non-Gaussianity. Intermittency basically is non-Gaussianity, how far it is from Gaussian distribution. And multifractality is just one aspect to describe such multifractality, such non-Gaussianity. Okay. And we already, another way to describe this discussed earlier, that was structure functions also. We had also and structure functions. Okay, so now we are finished with everything except for because even so I try to look a little into it. So it is a somewhat interesting topic indeed, because lately there has been suggestions to have generators based on triple electric effect of droplets. So droplets fall on a dielectric layer which is on top of a metal plate, and then electricity is created because of the impact, and there are some smart ways to make it into generator, and it can be quite efficient generator. Toma, was this about what you wanted?
Yes, I was thinking about it more in the context of cloud formation and thunderstorms.
Yeah, okay.
Because
In
they
cloud
have-
formation, it also, if you want to have, so I don't know if you had them, but Feynman lectures, lecture notes, which are freely available at Caltech website. There is one chapter where Feynman very nicely discusses it. Well, he says that actually how exactly that the friction of droplets is causing charges there is not very well known, and I don't know if that has changed significantly over Feynman's time up to now, but otherwise it's very nice reading, and I think it answers you quite many questions. So really recommend reading that chapter of Feynman's lectures about atmospheric electricity.
Okay, will do. Thank you.
Yeah. All right. This is nice reading. Feynman writes very, very nicely, and Just he sidetracks a little bit, like I am also doing the same thing, right? He also sidetracks. So he was supposed to speak about electricity, and they took one full lecture to speak about how atmospheric electricity works, how we have clouds and how a nice day. But I am not spoiling you. Just take your time and read it. Okay. All right, but then thank you for attending, and we have still one more week to go. So see you next week.
Thank you. Bye.
Bye. All right.